This video is on centrifugal force, also called centrifugal force. I'm going to see if I can explain it in under 2 minutes the way my physics teacher taught us. If you have a mass spinning around in a circle right here, and say there's a rope or a swing arm attached to that mass causing it to spin around in a circle, that mass wants to continue going in a straight line. So if you were to cut that rope at any point, then the mass would continue off in a straight line. But instead it's being pulled to the left in a circle. That inward pulling is called a centripetal force or centripetal force. You always have to have two forces, which means you have to have a force and a counterforce. You cannot have a single force acting alone. That would be like one hand clapping. So the counterforce to centripetal force is centrifugal force or centrifugal force. Since you have your two forces opposing each other, now you can get a reading on a scale right there. So if you had a tension scale on that rope, then you can measure what that force is. However, centrifugal force can also have another definition, which means it's a fictitious force. In the first example here, this is a third-person view, which means we're watching the action from outside of the experiment. But if we go to a first-person view, then that means we're part of the experiment. Imagine a large spinning disc like a merry-go-round, but there's no vertical bars that would get in our way if we're sliding across it. As this disc spins, we want to continue going in a straight line, just like that. But if this disc is spinning counterclockwise, we will have a constant force pushing us to the left and pushing us away from the straight line that we are trying to travel. Thus, we'll feel like we're being pulled to the outer edge of the disc, because as the disc continues to spin, we'll get farther and farther from the center of the disc and closer to the edge of the disc. There actually is no force that's forcing us to the edge of the disc. We will only have our initial force that forces us in a straight line, and the spinning disc will just cause us to deviate from that straight line. So centrifugal force can have two definitions depending on if you're talking about a third-person view or a first-person view. If you're dealing with a third-person view, then centrifugal force or centripetal force can be measured as mv squared over r. And since you always have to have two forces oppose each other to get a reading on a scale, centrifugal force will be equal to centripetal force. So this equation can be called either the centrifugal force equation or the centripetal force equation. And that's it. That's how we learned it. Then we moved on to optics or banked curve or whatever was the next chapter. But I'm going to go into more detail on this to give more of an intuition from here on out. These are just things I figured out on my own. And I picked up a couple of things off of Google and YouTube, but most of that information was contradictory to other bits of information or just wrong. The reason I'm making this video as an amateur that just dabbles in math a little bit for fun is because I couldn't find anything on YouTube that explained, that gave a full explanation of centrifugal force. And a lot of what I found was wrong. All right, so from here on out, it's just tidbits of information I picked up along the way or things that I reasoned out on my own. So for the third-person view, we have the inertial frame. And I guess you could think of this as the mass right here wants to continue under its own inertia in a straight line, but it's being constantly forced to the left around this circle. The opposing force could be called centrifugal force, also pronounced centrifugal force. It could also be called a normal force because it's a counter force or a reactionary force, or you could also call it an inertial force. Centrifugal force means center fleeing, which is actually not an inaccurate term because we have centripetal force, which is the force pushing in toward the center of the circle. And thus we have to have a counterforce pushing in the opposite direction. So centrifugal force is pushing away from the center of the circle, thus center fleeing. This center fleeing counterforce is also how centrifuges get their name, and I'll explain that later. If we move down to the non-inertial frame, which is the first-person view, this is where the outward force is considered fictitious because all this mass is trying to do is go in a straight line, but something keeps forcing it to the left, and that something would be friction from the disc. So that friction is what's keeping you from traveling in a straight line. The force that's needed to keep you spinning in a counterclockwise circle can be calculated with the equation mv squared over r. This mass is held in place on this disc by friction. It's the friction that provides the centripetal force, or the inward force, that forces this mass to turn counterclockwise. For every force, there must be a counterforce. So that means the outward force will increase also. That outward force also comes from friction. You can imagine that friction coming from, say, a bunch of holes in the surface of your disc, and that mass will have short pegs that fit in those holes. So as long as you don't provide too much of a force, then those pegs will stay in the holes and they won't pop out and the mass won't go sliding off. As this disc continues to spin faster and faster, then the force needed to force this object into a counterclockwise circle will exceed the frictional force, which means friction will no longer be strong enough to hold this mass in the same place on that disc. So this mass's inertia will tend to make this mass continue in a straight line, which means it'll start drifting outward on this disc, and that's how I drew this picture. This is the same concept if that mass was held in place by a rope. If the rope starts spinning the mass too fast, then your rope will break. Or if there was a bolt holding this mass in place on that disc, then the bolt would eventually break. And in under extreme conditions, then the whole disc itself will start to fly apart. I once saw a documentary about the land speed records that take place out on the salt flats. And some of those cars travel so fast, they have to have special metal wheels that won't fly apart from the inertial forces. This is also the reason why pizza dough thins out when people throw it up in the air and spin it. And I've seen videos of somebody taking a roller skate wheel or a skateboard wheel and using an air compressor to blow air on it really fast to make it expand, and then it tears itself apart. The individual atoms or molecules in that material, whether that material is a metal spinning disc or pizza dough or a rubber wheel, those individual atoms and molecules have mass, and thus they have inertia and want to continue going in a straight line or a straight path. At any rotational rate, the outer molecules will have a higher velocity than the inner molecules, and thus they will experience a greater inward force trying to pull them off of their straight path. Eventually that force is too great and the material rips itself apart because all those atoms and molecules are still trying to go in a straight path. If you multiply the radius of your wheel times 2, that appears to cut your force in half. Because the formula is mv squared over r, you're dividing by radius. Thus you're dividing by 2, so that looks like that will cut your force in half, or the centripetal force in half. But if you double your radius, then you're also doubling your velocity. But those two numbers don't cancel out because you have to square your velocity to get your force. So now you'll have 2 on the bottom for radius, you'll have 4 on the top for the velocity. 4 divided by 2 means you'll have twice the force, or twice the inward centripetal force. And if you multiply your radius by 4, then the velocity will be multiplied by 4 as well. But 4 squared equals 16. 16 divided by 4 equals 4. Thus you'll have 4 times the inward force. You could think of your mass as a large asteroid or space rock floating around somewhere in interstellar space. And let's say that big rock conveniently has a hole that goes all the way through it. So now we can run a rope through that hole and tie a knot and go back some distance and yank on that rope really hard, causing an acceleration or a sudden force, and you'll pull that rock apart if you pull hard enough. So that's what centripetal force does. It provides an inward force as if you're pulling on something with a rope. As I said here, it's considered a fictitious outward force because you're just trying to go in a straight line, but you're getting pushed off to the left. Technically, this force does push you away from the center of the circle, but it pushes you in a tangential direction compared to the center of the circle, and it's not pushing you directly away from the center of the circle. Meaning if you're this mass right here, you're going to get pushed straight ahead. But notice where straight ahead is, it's farther away from the center of the circle. And then you'll be right here. You'll still want to continue in a path that goes straight, and thus you'll be even farther away from the center of the circle. And that pattern continues all the way out to the edge of the circle or the spinning disc. And once you're no longer in contact with the edge of that spinning disc, you'll continue in your straight path because you won't have anything forcing you to the left again. I'll show a more intuitive example on the next page. I just realized I left the S off of person right there. As you can tell, I just scribbled this stuff down in a couple of minutes. And that sort of thing can happen in the morning if you're suffering from low serum caffeine levels. I suppose you could call that hypocaffeinemia. Imagine a ball in a tube, and you're going to fling this tube so the ball will rise up to the top of the tube and come out of the end of the tube. You'll have a force pushing on this ball that's pushing it in an upward direction compared to the center of the tube right here. The ball will exert a reactionary force or a counter force pushing against that. Again, you always have to have a force and a counter force. Newton's third law is that every action causes an equal and opposite reaction. And you can actually measure that force and that counter force by putting a scale in between the ball and the tube. So remember, you do always have to have two forces that oppose each other. Otherwise, you have one hand clapping, or a boxing match with only one boxer in the ring. Now, as this ball gets pushed upwards, it's going to be at this point right here at the top of the arrow. So notice how at the next picture here, the ball is a little bit higher. It's at a higher elevation, and it's farther away from the center of the circle or the bottom part of that tube. The force of flinging this tube continues to push this ball in a straight path. And now the ball will be a little bit farther from the bottom of the tube or the center of the circle. And notice here in the next picture, the ball rises up to an even higher point at the edge of that tube. If you don't have a tube, you could easily do this same thing with a board and a ball. Just put the ball at the bottom of a board and then fling the board, and the ball will rise up to the top of the board. Now the board here, or the tube, is pushing this ball directly to the left, and it still continues to push it in a straight line or a straight path. When this ball is no longer in contact with the edge of that tube or that board, then that ball will continue in a straight path. Now I'm going to show where a centrifugal force could be considered an imaginary force. As you put this ball in this tube or put this ball on this board and then you fling that board, it appears that there's a force that's causing this ball to rise up to the top of that board. There is actually no force pushing this ball up the board. The force is always perpendicular to the board. But that's where a centrifugal force is considered fictitious, because it appears that there's a force pushing this ball up the board or up the tube, and there is actually no upward force. And technically, this force is pushing the ball away from the center, but it's pushing it tangentially away from the center and not directly away from the center. So that's why the ball keeps getting higher and higher, or I should say it gets farther and farther away from the center. But as that ball or mass keeps getting pushed farther and farther away from the center, that board just stays right behind it and keeps pushing it farther and farther away from the center. So it makes it look like that the ball is actually rising up the board by some sort of force, but the ball is actually just being pushed tangentially to the center, and the board stays behind it and continues to push it. I think it's interesting to think, what if this swing arm right here, or this board, was at the bottom of a large cylinder, and maybe this swing arm went out, I don't know, really far, like infinitely far or something. And it was completely dark, so there were no lights, but this ball right here had a light in it, so it glowed. So as this swing arm started spinning around, all we would see is this glowing ball spinning around in circles, getting a wider and wider radius as it formed an outward spiral. Now maybe you can imagine, if this is a board that we're using to fling this ball, if we screwed another board perpendicular to the end of this board, now the ball is going to be stuck at the end of the board. Or if this is a tube, then we can say we just blocked off the end of the tube. If we continue to swing this tube around in a circle, we will have a centripetal force pushing in directly to the center of the circle. But we're also going to have a force to the left here of this board that's pushing the ball to the left. Here's another way you could visualize these two forces. We have the force to the left from the swing arm. We have the centripetal force that's pushing in towards the center of the circle. Imagine this swing arm is spinning around a cylinder, and there's a wall that goes around the edge of that cylinder, and that wall keeps the ball from flying off the bottom of the cylinder. Now we have our center seeking force of the centripetal force pushing straight down to the center of the circle. We always need a counter force pushing back against that. So that opposing force could be called a centrifugal force, a counter force, a reactionary force, or a normal force. We still have a force pushing this ball directly to the left, so we have to have a counter force pushing back against that as well. If this swing arm right here was the arm of a catapult, then that catapult arm will suddenly hit some sort of board or obstruction right there and cause that projectile to fly in a straight path. In that case, it'll fly directly to the left. And that's because we have a leftward acting force right there. But if this was a tube, like say a centrifuge tube, and the bottom suddenly blew out, then this mass will continue to rise up to the top of that tube, and it'll look like this situation right over here on the far right. And when that ball is no longer in contact with that tube or that swing arm, then it will continue in a straight path. On the next page, I'll show how a centrifuge tube gets its name. A centrifuge tube does its job and gets its name from the counterforce to centripetal force. This centrifuge tube will contain particles of different density. I represented the denser particles as solid black dots and the less dense particles as little circles. As this tube spins around really fast, it will have a centripetal force pushing everything in toward the center of the circle, and thus it will need a counterforce, which is labeled as centrifugal force, pushing everything against the centripetal force. And again, you always have to have two forces to oppose each other, Newton's third law. And you can measure that force in between the two by putting a scale in between the particles and the bottom of the tube. In reality, if you were to measure this force between the centripetal force and the counterforce of centrifugal force, you would need a large tube with some large masses in the tube, like balls or something, and then you could put a scale in the bottom of that tube. So these denser particles, as they get pushed against the edge of the tube with that counterforce of centrifugal force, then they are going to displace all of the lighter particles and force those lighter particles up to the top of the tube, or to the center of the circle, or to the center of the centrifuge machine. Thus, a centrifuge machine gets its name from using the counterforce called centrifugal force that forces all of these particles up against the bottom of the tube. A centrifuge machine simulates gravity hundreds or thousands of times Earth's gravity, and that centrifugal force, which would also be the centripetal force, can be calculated by using the equation mass times acceleration equals force. The particles with an increased density will have an increased mass, thus they'll have an increased force, and you can also use the equation mv squared over r. And in that case, you just replace the a for acceleration with v squared over r. The density of the particles is measured as mass divided by volume, so these denser particles will have an increased density that forces them to the bottom of that tube. I did 1 or 2 videos explaining the buoyancy laws, so you can see those videos if you want, but a centrifuge machine works by using those buoyancy laws. I just said here that this is a real counterforce that's pushing these denser particles to the bottom of the tube. This is not an imaginary force or a fictitious force, as Google said. If something is imaginary or fictitious, then that means it does not exist and it cannot exert a force. Centrifuge machines do their job by using a counterforce, and so does a bathroom scale. Most people think that a bathroom scale measures the downward force from gravity, which is mg, but a bathroom scale actually uses the reactionary force, which is the normal force that pushes perpendicular to the surface on which the bathroom scale sits. Let's say we bolt the bathroom scale to a board and put this board at a rather steep incline. And then we can put some sort of wedge here on the edge of the bathroom scale so that our mass cannot roll off of the bathroom scale. Now we'll get a decreased reading on the scale because the normal force is not aligned with the downward force from gravity. Thus, we are measuring the normal force or the reactionary force. So in the same way that normal force and weight are used interchangeably, when I was in physics class, we used the terms centrifugal force and centripetal force interchangeably, because they gave the same reading on a scale. One's just the force, the other one is the counterforce. And again, centrifuge machines got their name because of the centrifugal force, which is a real counterforce. It's not imaginary. Now imagine how long it took me to figure all this information out when everything I saw on YouTube and Google said that centrifugal force was not a real force, and that was the only information they would provide. When I outright asked Google AI how centrifuges got their name, whoever typed in the responses for the Google AI did not want to admit that centrifuges were named after centrifugal force. So they said that centrifuges got their name due to an imaginary outward effective force. So that's wrong because the force is not imaginary. If something's imaginary, it cannot exert a force. And secondly, that phrase was obviously intended to obfuscate, because the simple and correct way to answer that question is just to say that centrifugal force is the counterforce to centripetal force, and thus that's how centrifuges got their name. Once I learned this information in college, I didn't give it any thought since then because I just figured I understood it. But then my YouTube homepage was suddenly inundated by purported experts that were very interested in telling the viewer, like myself, that centrifugal force does not exist, and that was the only information they would supply. Some would state that centripetal force does not need a reactionary force, thus Newton's third law is not true. I got the same information from Google, so it took me quite a while to figure all this out. It's a bit strange that someone like myself that just dabbles in math is making a video that clearly explains centrifugal force. And every video I came across on YouTube gave pretty much nothing but red flags to indicate a fake educational video, meaning everything they said was just wrong or misleading, or they would just give random facts and not explain anything. For example, most of them would just say that centrifugal force is not real, and that was all the information they would give. That was mostly what I got from Google AI as well. So maybe there are some legitimate physics educational videos that do explain this, but none of them showed up on my search results. So that was a little weird because this information has been known for hundreds of years, and there's educational videos that explain just about everything.